Hello, class. Welcome back to lecture 22. This is the last lecture of the class, so congratulations on making it to the end. Today we're talking about Fourier series extensions, and so the idea is this. So far, to make the Fourier series for some function, you need a function defined on an interval negative p to p. So you got to have the function, you got to say what it's doing from there to there. But often in applications, we think about the x variable as instead being t, the time variable. And then we start our functions at 0 and not on the left side there. So we got to do something about that. Okay, so often in applications, we use time as the input variable. So f of t is only defined for t greater than or equal to 0. So you have functions like this, and maybe it just goes that way to p. So we can't do the Fourier series the way we have it now on this function. So what we need to do is extend the function. So to make Fourier series, we need to extend f of t. There are a couple ways to do this, and by extend I mean like make a function that's the same as f of t, except it is also defined on this side. But on the right side, it's the same. Okay, and then it's going to turn out that extending f of t is actually the same as just making a Fourier series, but it just depends on how you extend it, which series you make. Okay, and then so the reason that we're extending it is to make a Fourier series, but then the weird part is that making the Fourier series is what extends it anyway. Okay, so these are called half range extensions. Half range extensions. I'm not going to use that name very much, but that's what they're called. So the first way to extend the function is we can reflect it. And these are not the only ways that I'm going to talk about, but these are the three best for us ways. So we can reflect the function over the vertical axis. So if you have your function here, f of t, that goes from 0 to p, you can make a new function by just reflecting it over the y-axis. And I guess you could call that function g of t. So g of t is defined as this function. Now you could write this out as like a piecewise function and actually define g of t, but we don't really need to. The point is that g of t is the same as f of t on the right side, and on the left side it's just reflected. Okay, so now we have a function that's defined on negative p to p, so we can make a Fourier series for it. So that's what we're going to do next. So the Fourier series for g of t is, well, let's see. First of all, we should notice that this g of t, this tells us that g of t is an even function, which is good news when it comes to Fourier series. It saves us a lot of time. Why is it an even function? Because it's symmetric over the vertical axis, which is what we defined it to be. So we don't even have to check. We just know it is because that's what we defined it as. So it's an even function. So that's going to come into play when we create the Fourier series. Okay, so for an even function, the sign parts disappear. So we're not even going to bother writing them. And then this part, we can, I'm not going to skip any steps, but we can do this sort of doubling thing. And that's what we're going to do next. Oops, sorry, g of t. So we're taking the Fourier series of g of t, but then we're going to use a few tricks and reduce this thing down. So now we're in terms of t instead of p. I mean, instead of x, but it's all the same. Hopefully I don't miswrite something as an x later, which I probably will do. Okay, so this is the Fourier series for g of t, which is defined on negative p to p because g of t exists there, but it's an even function. So we can do lots of interesting tricks, like just integrating from 0 to p, just integrating this side, and then doubling the area like we did before. So let's go ahead and do that for some of these things. So if I double the first one, I just get 1 over p from 0 to p, g of t dt. Same thing happens over here. So I get 2 over p, 0 to p, g of t cosine and pi of pt. Those are my coefficients, remember? So we got that. Okay, so now the interesting part, you don't even have to deal with g of t anymore because these integrals are only using g of t from 0 to p. G of t is your original function. They're the same thing from 0 to p, which is where we're integrating. So now we can just replace these g of t's with f of t's. So we don't even have to deal with this function. And what this is saying is that if I just start with my, if I just do the Fourier sine series or the cosine series, which is what this is, of my original function, then I'll end up creating g of t anyway. So that's what this is really saying here, because this is equal to g of t. So the Fourier cosine series of f of t actually creates this extension g of t. So just to say it all again, so if I have a function that's only defined here, then I create the Fourier series, the Fourier cosine series, meaning I only do the cosine terms, I don't do the sine terms. And that will create, I can't redraw the same picture, but it'll create the g of t. Okay, so that's interesting to do. We'll do an example later. So that's the first way to extend a function. The second way, you might be able to guess based on what we just did, is we can extend f of t by rotating about the origin to create a different type of symmetry. So if you have a function that's only defined from there to there, you can make it symmetric. I shouldn't have drawn something so weird, sort of like that. Okay, pretend those are perfectly symmetric. So you can create g of t in this way. So g of t is defined on negative p to p this way. So now I can create a Fourier series for this g of t. But this time, g of t is an odd function by definition. So when I create its Fourier series, all the cosines will go away, and so will that first term. And then it'll turn out just like the last one. Okay. So then g of t equals 1 to infinity 1 over p. So I'll do what I did last time. So I'll just write out what it actually is. So the sine and the first thing disappear because it's an odd function. Sorry, the cosine and the first term disappear because it's an odd function. And then we're going to take advantage of that in a second to say something else. So now, since g of t is odd and sine is odd, we've done this before. The inside of the integral is now an even function because you can take out both negatives and then they cancel when you test if it's even function. And so now I can do my trick of, if I integrate an even function, I can just double it and do this. Oops, I don't know what I was writing over here. N pi over p there. Okay. And then same thing as before, g of t is the same as our original function on 0 to p anyway, the right side, which is where we're integrating. So in that integral, I can just change it to f of t. And so this is the Fourier sine series of f of t. And doing it creates this g of t. Okay, so that's what the idea. So doing the Fourier sine series, meaning doing the Fourier series, but only doing the sine terms of f of t creates g of t. Okay, so you create the extension by just doing the Fourier sine series like this. All right, and then the last way is we can extend by just doing the whole Fourier series, and that is going to correspond to just making a copy of the function. So something like this. Is what will happen. So you start with f of t, then g of t will be just the same function copied twice. Defined on negative p to p. And I'll just say how it's created. I'm not going to do all the same work I just did. But if you just do the whole Fourier series, of f of t, then it'll make this. So you don't get rid of the sines or the cosines, you just do the whole Fourier series. And you'll create g of t this way. Okay. So let's do an application where this is relevant. So let's jump into some applications, see how we could use this. So we're going to use springs as usual, just because they are the simplest to deal with. So suppose a mass m equals 1 over 16. is on a spring modeled by, so I'm just going to already include, the 16 is already included in this whole thing with the spring constant to get you 64. And there's no air resistance. And then there is this external force given by, so this is going to go on the right. This 1 over 16 is just going to make the numbers nicer later. Okay, so here's the external force. I'm just going to draw a graph of it. And it's something you could quite easily imagine existing in the real world. So it's some sort of machine that just every 1 second, or I guess every 2 seconds, as we'll see, just sort of does this force and then jumps and starts over. So it's going to look something like this. So it's just a straight line, and then after 1 second, it starts over. For 2 seconds, it does the same amount. And then after those 2 seconds, it starts over. So you can think about it as just a machine that punches or something, and it just does it over and over and over the same way over 2 seconds. So it just punches for 2 seconds, and then it just resets. So this is the external force. So this would be f of t, the external force function. So we need to write f of t somehow in order to write down the differential equation that we're trying to solve. So we need to solve. Oh, by the way, I changed. Normally when I do spring problems, I do p double prime plus, I would do this. Why did I change it this time? It's because we keep using p for something else. So I don't want to mix it up. So this time we're using y's. Okay, anyway. All right, so we need to solve y double prime plus 64y equals, you have to divide by the mass. That's why I put that 1/16 there, because this will just look nicer. But we need to solve this. And so I really need to describe f of t better so that I can solve this differential equation. So the first goal is to describe f of t. So first, and what we know is that Fourier series are good at this periodic motion. So if I can write down the Fourier series for something, then it'll look like this. But what's that something? Well, we need to extend f of t in such a way that the Fourier series gives us the correct force function. So just looking at the picture, we can see how we should extend it. So what I want is I want to define something on this side such that all these pictures look like copies of the first one. So all I have to do is do this extension. So that's going to be the function that we're going to take the Fourier series of. So we extend into the odd function by rotating about the origin. So this is our f of t from 1 up to 1. And we are going to rotate about the origin to create this odd function here. So then this is the g of t. You can think about this as g of t. And it is just the sine the sine or the Fourier sine expansion, Fourier sine series. So this is my g of t here. But what we just saw is g of t, if I do its Fourier series, if I just do the Fourier sine series of f of t, then that's how I get this g of t. And because the Fourier series is so wonderful, g of t is just this function, but its Fourier series is the whole thing, is all of these, because it just keeps repeating. So then the series will look like the original f of t. Okay, so the whole point is I'm just going to do the Fourier sine series of f of t. Okay, so first of all, what is f of t, or what is g of t here? So f of t is, well, this is a straight line with slope. What's the slope here? M equals pi, because you go over 1 up pi. So pi t is the function that I'm looking at. But now I'm doing it from negative p to p, and I'm just doing the sine terms. Okay. So then I get what I wrote earlier, 2 over p. Now we know p is pi. I'll plug that in a second. 0 to p f of t sine of n pi over pt. Sorry, so this is the coefficients. This is not the function. So I need these things. Now p equals pi. Okay, so 2 over pi integral 0 to pi f of t is pi t sine of n pi over pi t. So those pi's cancel, dt. So these are the coefficients I need to calculate to create the Fourier sine series. Good. Okay, so I need to use, unfortunately, integration by parts. So I'll do my little table method. Function that I'm taking derivatives on the left, function that I'm taking integrals of on the right, alternating sign. Derivative of pi t is pi and then 0. Integral of sine of nt is negative cosine of nt over n. And then one more integral of that would be negative sine nt over n squared. Okay. So then this integral equals this diagonal times that plus this one. Okay, so then I get pi t over n squared. Oh, sorry, pi t over n. And I guess there's a negative on that cosine, so I'll bring it out to the front. Cosine of nt. And then these negatives will cancel, so this will be pi over n squared sine of nt from 0 to pi. Oh wait, this p is already a pi. You could have left all the p's as p's before and then plug it in at the end, but either way is fine. Okay, so now I plug in pi. This becomes cosine of pi t plus sine of pi t which is going to always be 0, minus, and then if I plug in 0, that t will be 0, make everything 0, and sine of 0 is also 0. Okay, so now we do our normal trick, which is any multiple of sorry, I plugged it in for n instead. Whoops. Let's plug it in for t. So any multiple of pi with the whole number is 0, and this is -1 to the n. So then with this negative, you could write it as -1 to the n plus 1. So in the end, we get 2 over pi times pi squared over n times -1 to the n plus 1. You can cancel some pi, 2 pi over n, -1 to the n plus 1. Okay. I have an extra pi that was not supposed to be there. Crap. What is going on there? Sorry about that. 1 second. Oh, I know what it is. Do I know what it is? I have to pause and think. I don't want to waste time. 1 second. Okay, I figured out what I messed up on. A horrible mistake a long time ago. Guess what? P was not pi. Why did I do that? P was 1. We're going from -1 to 1. Ah, crap. So P equals 1. So that means got a lot to change here. This is why you keep P the same and then plug in 1 at the end so you don't make this kind of error. Fail. All right, so that P, that's a 1 there. And these do not cancel. So I just get n pi t because I've been dividing by 1. So then when I do integration by parts here, this is n pi t. So I have to divide by n pi. And then I have to divide by another pi, so this will be pi squared. So then over here, there should be a pi down here. There should be an n pi t, n pi t. And I'm integrating from 0 to 1. Epic fail. Okay. So now I'm divided by n pi there, and there should be n squared pi squared. Okay, and now when I plug in 1, I get n pi and n pi. But I'm dividing by pi here, and this t, I'm plugging in 1 also, so that should just be negative pi there. And this should be pi squared. Okay, so luckily these are still 0 because I'm doing, oh wait, they're not now, it's a little bit different, huh? Terrible. Okay, so, oh yes, they are, they're still 0. Because that t becomes 0 and then sine of 0 is 0. So this is still 0, good. Okay, so then this -1 to the n plus 1 is still there because of that negative and that cosine n pi. This is still 0, that's good. So don't have to worry about that. What's different now is that these pi's cancel here, which is what I wanted. And then I should only have oh, and then this 2 over 1 should have been 2 over 1 the whole time, not 2 over pi. So let's just change those. All right, so now, big finale, we got it. Okay, so this is just 2 times 1 over n times -1 to the n plus 1. Let's write it a little bit nicer. 2 over n times -1 to the n plus 1. So those are our coefficients for the sine series. So f of t, our force function, or we can call it g of t. I guess it doesn't really matter now because they're the same. On the right side, which is what we care about when we're solving a spring problem, g of t or f of t on the right side are the same. They're both that function I drew. So they have this as their Fourier sine series, which is what we're going to use as our force function. Okay, so it's n equals 1 to infinity, just the sine parts. These are our coefficients that we just figured out of each sine. And pi over p, p is just 1, t. Okay, so now our differential equation that we're solving is y double prime, 64y equals 16 times this. So all that work was not to solve the differential equation. All that work was just to write down the differential equation that we now need to solve. So this is what we're solving. And so I didn't give any initial conditions or anything, but so what would you would still do? So this is a problem where you get y equals yc, the characteristic solution, plus y particular solution. So we're just going to pretend that we have initial conditions because it's going to be way too big if we do. So we're not going to do that part. So we'll just do the particular solution part. Okay. So what's the particular solution? Well, we're going to use undetermined coefficients. We can still do that. So how can we do that? Well, remember, when you guess a particular solution, you guess something of the form of the right side. So the 16, I guess I can just multiply in and call it 32 here. Let's do that. So this right side is gonna tell us our guess. So our guess is that the solution should also be a series of sines. And so we're gonna guess a series of sines where we don't know any of the coefficients. And then we're going to plug in our guess and match coefficients. It'll work it out nicely. So I need the derivative and the second derivative to plug in. The derivative of each term is just a constant times sine. So all I have to do is take the derivative of sine, which is cosine, and then multiply by the derivative of the inside and pi, and then second derivative, same thing, but now derivative of cosine is negative sine. And I get another factor of n and pi. So these are what I'm plugging into my differential equation. So then we get this. And it looks pretty complicated, but we know how to combine series into one, so we're going to just do that. And then on the right side is this that we already know is our force function. So all we got to do is combine the left side, and then we can match coefficients. So the left side, they both start at 1, so we can stick them together nice and easy, and then we can factor out the sine and pi t. So this is going to be negative an n squared pi squared plus 64 an sine of n pi t. And so now we can match the coefficients of the sines. Okay, so that's what we're going to do. So then for these two series to be equal, we must have that negative a sub n squared pi squared plus 64 a sub n must equal 32 over n negative 1 to the n plus 1. So now we can solve for an. So all I have to do is factor out an and divide by, write like this, and divide by the rest. So negative n squared pi squared 64. So those are my ANs. So then that tells us the particular solution. And let me just write it a little bit nicer. So 32 over, let's do it as n times 64 minus n squared pi squared. 1 to the n plus 1 sine n pi t. So this is our particular solution of the differential equation. And so what I want to do is I want to show graphs this time. So I'm going to pause the recording and I'm going to share the graphs. Actually, first let me do one more example. We'll come back to that. That's going to be graphed for us in a second. Okay, so before that, so let's just think about if the external force was different. So same type of spring problem, but what if the external force looked like this instead? So it's a machine that sort of punches and then unpunches, I guess, like this. So then to solve the differential equation, again, we need the right side. We need to figure out the right side. So we would have to figure out how to extend f of t. So in this case, we would do the Fourier cosine series of, because what's going on is it's just copies of this function here. Which is what happens when you take f of t and you extend it in the even way by making it symmetric over here. So this would be the g of t that we do the cosine series for. Instead, negative 1 to 1. So we're not going to solve the differential equation, but let's write out what the force function equals this time. Okay, so then g of t will be, so 1 over 1, because this is 1 over p, integral from 0 to p, f of t dt, that's that first term, plus, and then the cosines. So 2 over p, 2 over 1, 0 to p, 0 to 1, f of t, cosine of n pi t. Because it's p is equal to 1 again, dt. So those coefficients are what we're going to have to figure out. If you want to write down the function for the force, if you want to write down what this thing is. Okay, so So this first integral we can just do. Integral from 0 to 1 of pi t becomes pi t squared over 2, which is from 0 to 1, so just pi over 2. So now we need to do this integral here to figure out these coefficients. And again, we're just going to use partial fractions. So that's these coefficients up there. Pi t cosine of n pi t, pi 0, plus minus plus, whoops, pi 0. Integral of cosine is sine, n pi t, then you got to divide by n pi. Integral of sine is negative cosine, n pi t, got to divide by 2 of these now. And then the integral is this times this plus that times that. So we end up with 2 times pi t sine of n pi t over n pi. Those two minuses will cancel, plus pi cosine n pi t over n squared pi squared from 0 to 1. And let's see, lots of stuff should go away as usual. Plug in 1, I get pi sine of n pi over n pi, plus plug in 1 here, I get pi cosine of n pi over n squared pi squared, minus plug in 0. This time's a little bit weirder. Not everything goes away. The first term goes away, but cosine of 0 is just 1. So that doesn't just go away that time. Okay, so then these pi's cancel. Sine of n pi, that's just always 0. This becomes negative 1 to the n. This pi cancels with that pi squared, and so I get 2 times negative 1 to the n over n squared pi minus, that cancels with that, pi, sorry, the pi cancels, 1 over n squared pi, common denominator, 2 times negative 1 to the n minus 1 over n squared pi. And so that tells me the force function on the right side, it's the same as g of t, so I can just write f of t, because I'm only concerned about the right side anyway. But either way, so now it's pi over 2 was that first term, plus n equals 1 to infinity. Now I got my coefficients here. Of my cosines. Okay, so then to solve, so we would solve the differential equation 16 times this thing. And you would have to solve it sort of the same way, undetermined coefficients, but we're not going to worry about it. Solve. What was this? It was 2 times negative 1 to the n minus 1 over n squared pi. These guys. Okay, so we would solve this. I'm not going to, not enough time. And then lastly, if the force function, we're not going to do this one, no time, but if the force function instead just looks like copies of this one, then you would have to do the Fourier series for f of t. not just the sines or cosines, the whole thing, to create the correct force function. Okay, so now I do want to show some graphs. So let me pause this recording so that I can go bring them up and then come right back. Okay, so here is the graph of some stuff on Desmos. So just to play around with this cool stuff. So first of all, this is when we extended in the odd way. So this was the g of t that we were looking at. All the names of the functions here, I just had to make different. Just worry about the picture. So this is the first situation. So what we did was we created the Fourier sine series, which creates this function. And you can slide the c to make worse or better approximations. So there's if c equals 1, but as you add up more and more terms, it looks better and better, like that line, like the function that we drew originally for the force. So this is just like the force happening over and over every 2 seconds. Okay, so then, then we solved that one. So that one I have the solution to. So that's the solution, the black line there. That's the particular solution. That's how it looks for the motion of the spring. Of course, this is not including the YC yet, but that's okay. All right, so then we had, if we extended the Fourier, if we extended the function in this manner, then the Fourier series looks like this. So it's a bit weird. It gets like too pointy where it's supposed to just be a turn. And that'll happen on these types of things. But again, different C's get you different amount of terms that you add up get you different, better and better approximations of the function. Okay, anyway, I just wanted to show that. And then this is how you would extend. You would have to do the Fourier series for this guy if you wanted to do the other type of function. Okay, so that's going to be it for today. See you next time, or I guess not. This is it. So have a nice life, I guess. See you later.